That is, okay, sorry, what you're seeing right now is rotational energy. We're not on that section. We're doing rolling objects, okay? Um, all right, rolling objects. So last year in Physics 1, you definitely learned that, when, objects roll, your wheels on your car roll, right? Um, and when an object rolls, okay, it actually has both types of energy, both translational and rotational kinetic energy. Okay. Okay, so it has both translational and rotational kinetic energy. There's two types of rolling. There's rolling without slipping, okay, and rolling with slipping, okay. So you either roll without slipping or you roll with slipping. And rolling without slipping is when the wheel is rotating and translating the entire time, rotating and translating with each other, sort of. So it's not skidding or anything. Rolling with slipping means that it is skidding. Okay. Here's some equations that you can use. If you're talking about a situation that's rolling without slipping, you can use that the velocity of the center of mass is equal to omega times r. That's your traditional equation, linear speed equation, right? And then you can also use that the acceleration of the center of mass is equal to alpha times r, okay? What you cannot use, okay, you cannot use that the force of friction is equal to mu normal force, okay? That is not allowed. Why not? It's because static friction. Okay, I guess there's a Windows update. It's not happening right now, though. Okay. Static friction has to be less than the value of mu sub f, or mu times f sub n. Okay. And the reason is because, well, um, if you know if static friction is acting, then that means that the wheel is basically falling over, and because it's circular, that's why it's able to rotate completely. Okay. What about if you're rolling with slipping? Okay, if you're rolling and slipping, then you actually can use the friction equation. Okay, because kinetic friction acts. Okay, kinetic friction is acting. Okay, um, and therefore then kinetic friction would have to be equal to mu f sub n. Okay, that's just friction rules. We've seen that before. When you are rolling with slipping, you cannot use the other two equations, v sub cm equals omega times r, or a sub cm equals alpha times r. You cannot use either of those two equations because rotation and translation are not synchronized. Okay. Okay. There's only one case in where you can use both of these situations at these where you can use all these equations at the same time, and that's only if you know, okay, static friction is about to break. Okay? In other words, that means you're rolling without slipping. Okay? But static friction is maximized. So it's at the maximum possible value, but you're still rolling without slipping. Okay? Friction only removes mechanical energy from the object if it's slipping. Okay, it's like the block sliding down an incline. If there's friction, right, then friction will remove the mechanical energy from that object. Okay. Okay. Now think about this. Okay. Think about this. You actually can, a wheel is basically a polygon with, unlimited sides, right? And what happens is basically we rotate a wheel or something that rolls without slipping. It rotates momentarily about the contact point with the surface. If you were to take a polygon, then it would roll by rotating about each point in contact with the surface, and it would go ka-chunk, 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 right? But the wheel, because it's so smooth, it doesn't ka-chunk, ka-chunk, ka-chunk. It rotates without any issues. Okay. Okay. Consider an object rolling without slipping up an incline, then down the incline. Now, what's kind of funny is that if the object is rolled, these free body diagrams are actually going to look the exact same. And the reason is because you have mg from the center of mass, okay? You have the force of friction, okay? And the force of friction is going up the incline, and I'll explain why. And then you have normal force from the plane, okay? And the reason why friction goes up the incline is because it's a clockwise torque, okay, to slow counterclockwise rotation, okay? So it's a clockwise torque to slow, because this is going to end up being a clockwise torque. It's currently rotating counterclockwise, but this is going to be a clockwise torque to slow down that rotation, okay? Now, on the other hand, this free body diagram is going to look the exact same, okay? Why does it look the exact same when it's rotating down the incline? Okay. Well, now it's because you have a clockwise torque, okay, and it's speeding up uh, clockwise rotation, okay. Because as you notice, if you let a ball go at rest on top of the incline, it's going to roll down. It's going to speed up its rotation to go down the incline, okay. Okay, this is an example. I mentioned the Claro wheel because I'm a fan of Claro now, okay. Um, And so this is the Claro wheel, which means nothing in the grand scheme of the problem. It has mass m, radius 0.25, moment of inertia 1/2 mr squared, held just above table. So how this works is that the wheel is held just above the table and it's spun up to an angular velocity, and then you drop it and it hits the table without bouncing, and then it starts rolling while slipping, but then it eventually transitions into rolling without slipping. Okay. Okay, and it gives us a coefficient of friction with the table, and we start out at angular velocity 30 rad per second, okay? Okay, to find the linear acceleration of the wheel, I'm just going to use forces, okay? F net equals ma. Well, the net force on it, the only force acting on it, is going to be friction, okay? So, what I need to do is I'm going to do F sub F equals ma, okay? Which means this is mu F sub n equals ma. And F sub n is just going to be mg because it's on a flat surface. So this is mu mg equals ma. And then you notice that the mass doesn't even matter in this problem. That's why it wasn't given to us at the beginning. So the acceleration is just mu times g. Okay. Mu is 0.2, g is 10, so the acceleration should just be 2 meters per second squared. Okay, that's the linear acceleration. To get the linear velocity, hey, wait a minute, I know that velocity is the integral of acceleration with respect to time. Okay, now hang on because this is going to get really difficult here. Okay, don't freak out. In order to find an expression for the velocity, I have to take my acceleration and integrate it. Okay, this is the part where things get kind of scary. So just hang tight. Okay, the velocity is equal to the integral of 2 dt. Oh, that's a tough integral, right? That's gonna be really tough for you to solve. And after enough agonizing pain, you're going to end up seeing that this becomes v equals 2t, okay? There's no need for the plus c because there is no initial velocity, okay? Linear velocity. There is initial angular velocity, okay? But we'll get to that. The angular acceleration of the wheel, okay? Well, all I got to do is use my torques, okay? I alpha, okay? And then when I solve it out, this ends up becoming r times the force of friction, because that's what's providing torque, equals I alpha. And then if I actually plug everything in, r mu mg equals 1/2 mr squared times alpha, okay? What I'm actually going to do, okay, is actually no, I'm going to leave it like this. Oh, sorry, alpha. That's right. I need alpha there. Okay. What you'll recognize is that here you can actually cancel out your m's on both sides, just like last time, but you can also cancel out one of your r's on both sides, okay, which is pretty cool. And I end up getting that mg equals 1/2 r alpha, okay. And then I just plug everything in here, okay. This becomes 2 mg divided by r. Okay, so then alpha is just 2 mg divided by r. So when I plug everything in, I get 2. The mass is, oh sorry, this should be mu right here. Why is that mu? Okay, 2, the mu is 0.2. G is 10. And then r, the distance we got earlier, the radius is 0.25. Okay, that was given to us in the problem text. And we should end up getting alpha will be equal to approximately 16 rad per second squared. Okay. Okay, and then you're going to do the same thing to get angular velocity. You just have to integrate this. Now, it is a little bit more weird. Okay. Oh, sorry, not that. I meant to do omega. Okay. Omega equals the integral of 16 dt. Okay. So now I'm just going to take the integral and I end up getting that omega is equal to 16t, okay, plus c. Now here's the thing. We do have to have that constant integration because we actually do have an initial angular velocity. Now what's happening, okay, is that you have to know, is this plus c going to end up being positive or negative? Well, we do have an initial angular velocity, but we're not gaining angular velocity as we're not gaining angular velocity as we spin, okay? The wheel is initially rolling and translating. It's rolling really fast, but then eventually it slows down. So the the angular velocity should actually be decreasing. So we can start at 30, but then we have to subtract 16 from every second that we go. So this ends up being omega equals 30 minus 16t, okay? At what time does the wheel begin to roll without slipping? Good question. Let's figure that out. Okay. Okay. Well, we can use v equals omega times r because the motions are synchronized now. Okay. And I'm just going to plug in my expressions here. V is 2t, okay, equals 30 minus 16t times r, which is 0.25, okay? I need to solve for t here, okay? Well, I need to solve for t here. So what I'm going to do is I can distribute my 0.25 and I get 2t equals 7.5, okay, minus 4t, okay. And then I should end up getting t by itself. So if I add that to both sides, I get 6t equals 7.5, and I should end up getting that t will have to be equal to 1.25 seconds. Okay. Okay, and the final part is how do you determine the kinetic energy? I'm not going to do the whole thing because it's really not that bad, but you just take initial kinetic energy minus final KE, okay? And your initial, or sorry, equals delta E KE, okay? And then when you calculate this out, you have to understand that the initial kinetic energy is all rotational because this is before it hits the table. The final kinetic energy is translational and rotational, okay? Okay, so then you would, if you figure out the difference, you subtract and you get however much energy is lost in the course of that action. Okay, is that the end of that? No, there's one more problem. Okay, you have an object of mass m, radius r, moment of inertia kmr squared, rolls from the top of an incline of height h, length x, and angle theta. Coefficient of friction with the incline is mu, which is high enough to prevent the object from rolling from slipping. Okay. Well, the object, okay, it's going to go from GPE to both KEs. Okay. So I'm going to do MGH, okay, equals 1/2 MV squared plus 1/2 I omega squared, okay? And if I substitute, I get MGH equals 1/2 MV squared plus 1/2 I is going to be KMR squared. Omega, I'm going to replace omega here because I got two different types of velocity and I don't even know what one of them is. So I'm going to replace omega with v squared over r squared, okay? And that's because it's squared, right? Omega is just v over r, and then I square it, so it's v squared over r squared, okay? Okay, and then you'll notice a ton of stuff is going to cancel. M, okay? M cancels out. R cancels out, okay? Okay, and then you end up getting this really, really nice looking equation. It's really not, you know, not that bad. You get GH equals 1/2 v squared, okay, plus 1/2 k v squared, okay? And then you can factor out the 1/2 v squares if you want. You can get GH equals 1/2 v squared, okay, times 1 plus k. Okay, and then you have to solve for v, okay, because we're trying to find the linear velocity. And that, I'm just going to show you what you end up getting, okay? You have to divide both sides by 1 plus k, multiply both sides by 2. You should end, and then square root, and you should end up getting that v would be equal to root 2gh, okay, over 1 plus k. All right, and that's what you should end up getting for that one. Okay. Determine the linear acceleration of the object on the incline. Okay, so to do that, what I can do is I can actually use kinematics. Okay, if I can use the no time equation, that would be great. Okay, and I actually can. Okay. Okay, initially the object has no initial speed, so this part should be nothing. Okay. And then what I end up getting is I need to get the acceleration by itself, but I also figured out earlier that v is this. So I'm going to plug this in for v, okay? And I end up getting 2gh over 1 plus k, all right? Okay, and set that equal to 2ax, okay? And then you'll notice, okay, well, my 2's can cancel out, so I can get rid of those. Not a huge deal, okay? And then you'll see that all I have to do is divide by x. So what ends up happening is you get this expression, which is a equals gh over 1 plus k times 1 over 8x, okay? Now, here's the thing, okay? I'm writing it like this for a reason, okay? I'm writing it like this on purpose, okay? Because you can rewrite this as being a equals g over 1 plus k, and then you actually can move the h over the x, okay? And when you do that, you're going to notice that you've got h over x opposite over hypotenuse. Hey, wait, isn't that sine? So this is the same thing as saying g, okay, 1 plus k is the same thing as sine. So sine there, okay? Okay, the force of friction acting on the object as it rolls down the incline, okay? What we're going to do is we're going to have to do our net forces, okay? We're going to do traditional Newton's second law. That's going to be the driving force that brings it down the incline, which is mg sine theta, okay? Minus the force of friction, okay, equals ma, okay? Now all I got to do is get the force of friction, that's what I'm looking for, okay? So I end up getting, let's see, mg sine theta, okay, minus ma equals force of friction, okay? Okay, well, I've already figured out, okay, that A is just this, so I'm going to do that, okay? I end up getting mg sine theta, okay, minus, okay, um, mg over 1 plus k sine theta. Okay. Okay. Again, I'm just substituting a for that g over 1 plus k sine theta. And set that equal to the force of friction. Okay. Okay. You'd have to solve it out a little bit. Okay. I can factor out mg sine theta from all these terms, so that's what I'm going to do. Mg sine theta, okay, times 1 minus, I guess it would be 1 over 1k, 1 plus k. Okay. Oh, and that would be equal to the force of friction, okay? Um, Now, I can then make a common denominator with 1 and turn this into 1 plus k over 1 plus k. And that's actually what I'm going to do. I'm going to do mg sine theta, okay, 1 plus k over 1 plus k, okay, minus 1 over 1 plus k. And you have a common denominator, so you can actually subtract them just fine. It ends up being the force of friction will be equal to kmg sine theta, okay, over 1 plus k. All right. Okay, now suppose that mu is small enough so the object slips as it rolls down the incline. Now we can use some of our other equations, okay? So for example, I can use the force of friction is equal to mu F sub n, okay? And if I use F sub n, I have to use mu mg cosine theta, okay? Okay, so then what I can do is I'm going to, again, set up a balanced forces equation, okay? Mg sine theta, okay? Mg sine theta minus mu mg cosine theta, okay? Equals ma, sorry. Okay, and then I just figure out what the acceleration is. I've got m in everything, so I can cancel those out, and I end up getting a nice simple equation, okay? If I simplify it, it ends up being a equals g sine theta minus mu cosine theta, okay? Okay, and that's my acceleration. That's all I got to do to get the acceleration. The angular acceleration, what you can do is you can divide that whole thing by r, which is fine, or you can use, or sorry, I guess you would, you could do it with r, but instead I'm going to use a torque approach. Okay, the net torque is equal to I alpha. Okay, where r times force of friction is equal to kmr squared times alpha. Okay. And then when I replace the force of friction, I get r m or sorry mu mg cosine theta. Okay, equals kmr squared times alpha. And what you'll notice is that you've got m on both terms. Okay, you've got one r that you can cancel out. Okay, and you will end up getting, okay, alpha equals mu sub g cosine theta over r. Okay, not quite the same as the previous problem with just r on top of it. Okay. Okay. And finally, the minimum value of mu to keep the object to roll without slipping. Okay. Well, first off, I'm so sorry. I don't know what just happened right there. If I do r force of friction equals I alpha, okay, then what I can do is I can just rewrite again r mu mg cosine theta, okay, equals I, which is kmr squared, times alpha, which I'm going to rewrite as a over r squared, okay? Oh, sorry. I don't need to square it right there. Okay. Okay. And what you should notice is you got your m's on both sides. You can actually cancel out the r's completely because one of your squareds cancels out right here, but then the other r cancels out at the end on the other side of the equation. Okay. And so we should end up seeing that this becomes mu mg cosine theta, okay, equals k, really or ka, sorry, okay. Well, I know acceleration from up here, okay. So now what I'm going to do is mu mg cosine theta equals k times possibly, or sorry, k g sine theta mu cosine theta. Okay, g sine theta minus mu cosine theta. Okay, I can distribute my k. This gives me mu mg cosine theta equals kg sine theta minus k mu cosine theta. Okay. You got g in every term here, so you can cancel it. Okay. Oh, sorry, this should be mu g cosine theta. Okay. You got g in every term, so you can cancel it. Boom, boom, boom. Okay. And you end up with mu m cosine theta. Okay. Oh, and you should have. Oh, I guess this m. Oh, sorry, that m canceled. I don't even know why I had that m there. Like it canceled out. Sorry, I'm losing my mind right now. I'm so tired. Okay. Mu cosine theta equals k sine theta minus k mu cosine theta. So then you end up on the left-hand side, it ends up being mu cosine theta. Okay. Um, and then right here you have k sine theta minus k mu cosine theta. I'm going to get mu on the other side, so I'm going to add that to the side. So it ends up being mu. Let's see if you can see that. It ends up being mu cosine theta plus k mu cosine theta equals k sine theta. Okay, and then you go from the two mu's to one. So I'm going to factor out mu, and I can actually factor out cosine theta too. So I end up getting mu cosine theta mu cosine theta parentheses. This guy was by himself, so it's just one. This guy had k with him, so he brings that there too. Okay, and so that equal to k sine theta. Okay. If you divide both sides by cosine theta, okay, by the cosine theta 1 plus k, you'll end up seeing that you get mu equals k sine theta over cosine theta 1 plus k. And you'll notice, hopefully you notice this, that the sine and cosine on top of each other, that's tangent, okay? And then everything else can remain. So this is going to be that mu would be equal to k over 1 plus k tangent theta, okay? And that's the expression that you end up getting for the minimum value of mu, okay? Oh boy, that was a lot, wasn't it? Okay. Well, next time we'll look at angular momentum, okay? All right, so have fun.